So all chemical equations are associated with some sort of enthalpy. And they can be written as you see below here, the reaction between hydrogen gas and oxygen gas to form water. And the delta H for that reaction is negative 483.7 kilojoule. What that means is that for one reaction, or 1 mole in this case of oxygen, you will generate and release 483.7 kilojoules. You understand that the sign here is negative, which means energy is released from this reaction to the surroundings. If that was negative, energy would be absorbed by this reaction. And so you have a number of conversion factors here. This is for every 2 moles of, it requires 2 moles of hydrogen gas to balance this reaction, so that it means if 2 moles of hydrogen gas are consumed, then 483.7 kilojoules are released. So the stoichiometry is important of a balanced reaction, right? So 2 moles of water, it's in a 2 to 1 to 2 ratio. And when that all is balanced and is done on a molar scale, we refer to that as molar enthalpies for these reactions. And another thing that's really important is that the phase labels also matter, right? There's a difference between forming gaseous water and liquid water, and then the delta H for that particular reaction would change. And now that you have this value for delta H, you can manipulate that just like you would any simple mathematical quantity, right? So if you did half the reaction, right? So if you just took 1 mole of water, then you just require, of course, half a mole of oxygen. Then you only get half the energy released. So that it just makes perfect sense. And then you can take that even further and cut it in even smaller. If it was for half a mole or 0.3 moles, you can just use it as a conversion factor. So if I ask you how many calories or kilojoules would be released if we use 0.334 moles of hydrogen, what you would do is, and you can do that based on the initial reaction, right? You would say that there is for 483.7 kilojoules are used for 2 moles of H2O, right? So this you have to then take into consideration that there are 2. Okay, so you can also reverse that reaction, right? So this is still the same reaction. You just flip it around. So instead of combining hydrogen and oxygen, you're decomposing water. Then all that happens is there's a sign change, right? If 483 kilojoules are released when water is formed, that means 483 joules are required to break water apart. That just is not too complicated. And so we can do reactions, we can do calculations using the same reaction, asking how much heat is evolved when 4 moles of oxygen react. You simply say 4 moles of O2, and you set it up just like you would millimeters to centimeters, or grams to kilograms, and pounds to I don't know, ounces. So you want to divide by moles of oxygen, and so there's a 1 here, and you multiply by the kilojoules, minus 483.7 kilojoules. So that's simply 4 times as much, and that would be negative 1,000. Sorry, that's 1,934.8 kilojoules. And there's the answer for that. Or how much heat is evolved when 12.7 grams of hydrogen react. Then you need to make the connection between the molar mass and the moles again, right? So you're going to have to take the 12.7 grams of hydrogen times 1 mole of hydrogen divided by 2 grams of hydrogen. That's just the molar mass of hydrogen. and then you multiply by minus 483.7 kilojoules divided by the 2 moles of hydrogen for a reaction, right? So 483.7 kilojoules are released for every 2 moles of hydrogen gas that reacts, and so you get a minus 1,524 kilojoules here. Right. Okay, so there's a table in the back of your book. It's in the appendix, and I encourage you to, it lists all the standard enthalpies, right? So there's actually an enthalpy of formation that is a delta H of delta H little sub f here, which is the delta H of formation of many different substances. And so what that means is, if we go back here, and there is actually a delta H of formation associated with H2O, and it's not necessarily minus 483. Now what that means is that for, let's pick a different substance just for fun. Let's say you want to make carbon dioxide. The delta H of formation would be based on the reaction of the elements in its natural phase. So carbon exists as charcoal, and oxygen is diatomic in its natural phase, and it's gaseous, so it's carbon solid, and so the delta H's of formation of these reactants, they each have a value of 0. Okay, so the delta H of formation from the table that you look up for carbon dioxide, which happens to be minus 393.5 kilojoules. Let's take a look at the table. Okay, so there's a ton of them out there, right? So we're not after delta G and S. We are after here delta H of formation. You need to be able to look up those values, right? And as you see, as you go through this table here, there are 2 elements or compounds that have, and they're elements that have a value of 0 next to them here, right? So bismuth is a solid in its natural phase, right? And boron is also a solid, and it's not diatomic, and it's in its natural phase. So it gets a value of 0. And then if you go to hydrogen, it'll be H2 in the gas phase. Oxygen, it'll be H2 in the gas phase. Iodine would be like I2 as a solid, and so those exist. Those all get the values of 0. And what you do then is, and so that's what that means here, right? So the delta H of formation of the elements in their natural phase is so the delta H's for anything else is then simply you pick it apart here. Hydrogen and oxygen, you put them over on the left side and you put them in their natural phase, and so the delta H of formation here, minus 241.8 kilojoules, is based on the reaction shown. Same for NH3. You can do this with any compound, and even 3 and 4 atoms, so you just have to add. You just have to find what they are. If you don't know, you don't have a good feeling for it, what they are, right? And so the value listed here for ammonia is negative 45.9 kilojoules per mole, right? Okay, and so and then since this reaction, once it's balanced, has 2 moles of ammonia produced, then the delta H for the reaction here is negative twice that, negative 91.8 kilojoules. Okay, so once again, that's just summary here, the standard enthalpies. Alright, need to move on. So, and you can calculate the delta H for a particular reaction, even if the reactants are not elements in their natural phase, by simply adding up all of the delta H's for the products. So in this case, it's just negative whatever it says, 285.8 kilojoules per mole for water here. And then adding up all of the products, which happens to be 0 and 0 here, fortunately, so that makes our calculation easy. But this is called Hess's law. So it's the enthalpies of the products times their coefficients from a balanced reaction. That's what N is here, minus the sum of all of the delta H's of formation of the reactants. Now let's look at something where we don't deal with zeros. Okay, so I highly suggest that you pop up that table. There, they have them on. You have them online too, but you can't use online for an exam. So you do need to have these enthalpies for your exam handy from your book. Okay, I think I might be able to upload a file for that, or a website that you can print possibly. So if we now want to do the delta H for this reaction here, I want to see the delta H for the reaction for this balanced reaction. So what we have here then is we need to look up the standard enthalpy of carbon dioxide, multiply that by 2, look up the standard enthalpy for iron, which is going to be 0 in this case, multiply that by 2, and then subtract the enthalpy of carbon monoxide and iron 3 oxide. Now when I go to the table, and you would go to iron, and then under iron you would find iron 3 oxide, and iron 3 oxide has a delta H of minus 825.5. That's just from that table. And iron is 0 because that's in its natural phase. Carbon monoxide has minus 110.5, and carbon dioxide is minus 393.5 kilojoules. Okay, and then all you do is you add up the delta H's here, right? So 3 times minus, that's here, 395 plus 2 times 0, right? So that's 0, not a problem. You add that up and then subtract it from the sum of the enthalpies of the reactants, right? And so we have 1 times minus 824, and then 3 times minus 110.5. And that gives you a delta H for this reaction of 23.5 kilojoules per mole. So this is an endothermic reaction here, right? Okay, so you should be able to do that. It's not very difficult. Just work a couple from the book, and make sure you learn how to use the table, and watch out for the phase labels, because the phase labels are important. Okay, so if I was to ask you, if I wanted to make it more complicated, I could say calculate the heat required to decompose 10 grams of magnesium carbonate. Okay, so this is magnesium carbonate. It's decomposing to magnesium oxide and carbon dioxide. And if I look up the delta H's for carbon dioxide in the gaseous phase, you find that's minus 393. Sorry. Yeah, well, that's correct, but yes, minus 393. And magnesium carbonate is minus 601, and carbon dioxide, we already have. Magnesium oxide is, yeah, okay, so magnesium oxide is negative 601.6, and magnesium carbonate is minus 1111.7 kilojoules. The units here are all kilojoules. They're kilojoules per mole, but the per mole goes, of course goes away when we calculate the delta H for the reaction. Okay, so it's just for the reaction, right? And so the one thing you want to do is now simply and if you calculate that, it's plus 116.6 kilojoules. This is already balanced, right? We've got 2 and 1, it's 3 carbonates, 3 oxygens, and Okay, thinking of recording this again because messing up too much. All right, so then what you need to do, you need to of course convert the 10 grams times 1 mole of magnesium carbonate. You know what? I'll record it next year. Divided by 8 at 1, 81.3 grams equals 0.123 moles, and so all you have left then is to multiply that by this number here, 116.6 kilojoules, and your answer is then 14.34 kilojoules for 10 grams, right? So all of this is related by the molecular weight, and the moles are of course connected to the delta H of the reaction based on the balance. This is for 1 mole of magnesium carbonate, but 10 grams is not 1 mole, 10 grams is roughly a tenth, so that's what you would expect, about a tenth of the energy that's normally released. Okay, so we can do some other fun stuff with these concepts. We can actually look at delta H's for reactions and combine reactions to come out with a new delta H for a new reaction here, right? So if I experimentally measure the energy released or absorbed by the combustion of graphite here, right? So we've got graphite, and I can determine what delta H for that is, and I can also do the same thing for carbon dioxide decomposing to carbon monoxide and oxygen, and so I get at a second value for that. I can combine these reactions here, right? So you see that you have carbon dioxide as a reactant here, and it's a product on the other side, so that actually would cancel each other out. And then you just pull it all down. You still have the carbon, and you have oxygen here, and so you have oxygen, and I missed it here. You have oxygen as part of the product, but only 1 oxygen as a reactant, so that oxygen stays, and the other product is of course 2 carbon monoxides. And so because we needed to multiply this entire reaction by 2, we need to take 2 times the amount of delta H for the first reaction and only 1 times the delta H for the second, right? See, these 2's were already for 1 balanced reaction. We needed them to balance that. Now, we needed to take this one twice, because otherwise we wouldn't have come up with this reaction here, right? So we needed to multiply that by 2 so that we can cancel the 2 carbon dioxide molecules here. That's the only reason why we did that by 2. Okay, so let's take a look at a reaction that we can do and maybe make more sense of it, right? So if I wanted to determine, if I ask you on an exam to determine the delta H for the reaction shown here, and it is balanced already, aluminum and manganese 4 oxide forming aluminum oxide and manganese metal. So it's a nice redox reaction. I told you that there are 2 related known reactions shown here. Combustion of aluminum and the combustion of manganese, and I provide you with delta H's. Can you determine, based on the information provided, what the delta H for that reaction is? Okay, so that's actually not that hard. What you want to do is you want to look at the products and the reactants of what you're after, which is this. This is where we want to know the delta H of. And so you realize that you have aluminum as a reactant, and this first reaction has aluminum as a reactant, so it's okay. And then we have aluminum oxide as a product. Okay, so that is on the correct side already. But when I look at the second reaction here, I have manganese, which is part of the product. And so I need to flip this reaction so that it works out. So I'm just going to reverse that. So MnO2 decomposes to make manganese and oxygen. And then what happens here, of course, the delta H now reverses. So this is now plus 521 kilojoules. Now I will write the other reaction below. 2 times aluminum plus 3/2 oxygen goes to Al2O3. Now we're going to have to make sure that we cancel. We only want the aluminum in the equation, and we need 4 of them. So it sure looks like we're going to have to multiply this by 2, right? Which would also furnish 2 aluminum oxides, which is what we have here. And the other reaction here, we have we need 3 manganese oxides, and so we just multiply that by 3. Okay, and when you do that, you actually do arrive at the reaction that we're after. 4 Al solid, right? Because 2 times 2 is 4, and then we have 3 MnO2, and then 2 times 3/2 is 6 oxygens, right? And sorry, it's 3 O2s. If I multiply this by 2, I get 3 O2s, and there are 3 O's here, so that actually drops out, which is convenient. And then we get 3 Mn and 2 Al2O3. And if I now want to know what the delta H is for that reaction, I need to take this value times 3 and this value times 2. I had to multiply that reaction by 2, so I need to multiply that by 2, and this reaction by 3, so I multiply this by 3. And then you have to just simply add them together, and what you get is the delta H for that reaction is going to be minus 1,789 kilojoules. That would be the delta H for the reaction shown below. Okay, I don't have a heck of a lot left, but this is a nice break. So when I come back, I'm going to look at bond energies and the crystal lattices of ionic compounds.